Hello and welcome. In this video, we're going to talk about concavity and the second derivative test. Our objectives in this lesson are that I can determine the intervals on which a function is concave up or concave down and find points of inflection, and I can use the second derivative to determine relative extrema. So let's go ahead and jump right in. The second derivative tells us about concavity. So before we jump into the calculus behind this, let's talk about what concavity is. Concavity is the basic shape of a graph, or the curvature that we see when we're looking at it. Is a graph opening upward or opening downward? So if we look at this graph here, we can see this red portion of this graph. It almost looks like a sine or cosine graph. The red portion of this graph is concave up. It's almost like a smiley face. It's opening upward. This blue piece to the left is opening downward. It's concave down. It's almost like a hill, and this is sort of like a valley. So we say a graph that opens upward or is cup-shaped is concave up, and we're seeing that here. And a graph that opens downward or looks like a frown is concave down, and we see that here. And the second derivative actually tells us about concavity. So if the second derivative is positive, that's what tells us that our original function is concave up. And if the second derivative is negative, that's what tells us that our original function is concave down over those specific intervals. If we're talking about tangent lines of curves, a tangent line on a portion of a graph that is concave down would have to be above the graph so that it only could touch the graph at one place. Similarly, if a graph is concave up, a tangent line would have to be below that graph in order to touch the curve only once. So concavity has to do with the second derivative. The second derivative positive means that we have a concave up portion of our original graph, or a cup, and a concave down frown means that we have a second derivative that is negative. We also have a special name for the place where they are changing from concave up to concave down, or vice versa, and that's going to be called an inflection point, and we're going to get to that in just a little bit. So before we get to the calculus of finding the intervals in which a function is concave up or concave down, I really want to make sure we pause and understand from looking at an original graph what the concavity is. So if we look at this graph on part A, we can see that it's concave down over this portion of the graph. And then it starts opening upward to be concave up. Go ahead and pause the video and highlight the intervals over which the function that you're seeing is concave up and concave down in B, and try to use two different colors. All right, hopefully you have had enough time to do that. This function is concave down all here and all here, and somewhere in between those two, it's changing and becoming concave up over that middle section. It's not clear from this graph exactly where it's switching from one to the other. We're going to learn the calculus to help us identify that place. But we can see from the graph the shape is the concavity, and we're going to learn how to use the second derivative to identify those intervals. As I mentioned before, the place where we switch from concave up to concave down has a special name, and that name is inflection point. An inflection point is where we're changing concavity. What that's going to mean about the second derivative is that the second derivative is going to change sign. Either it was positive and then negative, or it was negative and then positive. So similarly to the first derivative test, we're going to need to know where the second derivative is 0 and where it's positive and negative, so that we can identify these different pieces of information about concavity in our original function. So an inflection point is a place where the second derivative is changing sign, and what that looks like in the graph is where our graph is changing concavity. So let's go ahead and tie together the pieces of information that we're saying about the second derivative all in one place, and then let's look at an example. All right, so what does our second derivative tell us about our original function? Well, we already talked about if the second derivative is positive, that means the original function is concave up. If the second derivative is negative, that means our original function is concave down. Where the second derivative is changing from positive to negative or from negative to positive. It doesn't matter which way it's changing. Those are going to be our inflection points. So similar to the first derivative test, when we're looking at intervals of concavity and points of inflection, we're going to first find the first and second derivative and figure out what x values are making the second derivative 0, or what values are making the second derivative undefined. These are going to give us our possible inflection points, or our pips. This is like a critical number in the first derivative. Then we're going to go ahead and make a sign chart with our second derivative and use that sign chart to identify the key information about concavity and inflection points. So let's go ahead and work through this example. Go ahead and pause the video and find both the first derivative and the second derivative for the example in the box. So here we have our first and second derivative, and we're going to go ahead and set our second derivative equal to 0 and solve. That's going to give us two possible inflection points at x equals -1 and at x equals +1/2. So we're going to list those off to the side. And then we're going to make a second derivative number line, and we're going to include those two values on the second derivative number line. So we're going to plug in something smaller than -1, like -2, and we're going to plug that into our second derivative. I'm going to highlight that so I make sure I plug it into the right place. If I plug -2 in, I'm going to get 12 times 4, so 48, minus 6 times 2 is 12, minus 6. And this is going to be a positive value, 48 minus 12 minus 6. I'm going to plug 0 into our second derivative. That's going to give me -6, so that's going to be a negative value. A friendly number that's greater than 1/2, like 1, is going to give me 12 plus 6 minus 6, which is also going to be a positive value. So just like we did with the first derivative, the second derivative is telling us about concavity. So where the second derivative is positive, those are the intervals on which we are concave up in our original function. So that would be -infinity to -1 and 1/2 to infinity. And the justification there is that the second derivative is positive on those intervals. Similarly, where the second derivative is negative, in this case, -1 to +1/2, that's going to tell us where our function is concave down. So again, the second derivative tells us about the concavity of the original function. Where it's changing at both of these x values, so at -1 and +1/2, those are where we would have inflection points, where the graph would start changing its concavity. And our justification there is going to be because f double prime changes sign at those two x values. So let's recap what we just pulled, this information in a different way, and then work through a couple more practice problems. So what we have just learned is that we can use the second derivative to give us information about the concavity of our original function. So what we're going to do first is find our second derivative and what makes it 0 or undefined. These are our possible inflection points. We're going to create a sign chart using the second derivative and testing values in the second derivative to determine where it's positive and negative. That will allow us to describe the intervals of concavity. If the second derivative is positive, that means that our function is concave up. If the second derivative is negative, that means that our function is concave down. And where it is changing from positive to negative, those are going to give us our inflection points. Let's look at a few more examples. Okay, so step 1, we're going to find the first and second derivative. So the first derivative is going to be 12x minus 12x squared. The second derivative is going to be 12 minus 24x. That's going to be defined everywhere, so let's go ahead and figure out where it is equal to 0, and it's going to be equal to 0 if x is positive 1/2. So in this case, we only have one possible inflection point, which means we only have one possible value that we need to consider when we're making our sign chart. So let's go ahead and plug in a friendly number smaller than 1/2, like 0, and we're plugging that into our second derivative. If we plug in 0, we get 12, which is a positive number. A friendly number larger than 1/2 would be 1. 12 minus 24 is going to give us a negative value. And then we can use this information to fill in the blanks on the left-hand side. We are concave up where the second derivative is positive, which is negative infinity to positive 1/2. Our justification is because our second derivative is positive. We are concave down where our second derivative is negative, so concave down from positive 1/2 to infinity, and our justification is that our second derivative is negative. We have an inflection point when x is 1/2 because that is where the second derivative is changing sign, in this case from positive to negative. But all we have to say is that the second derivative is changing sign before and after x equals 1/2. Again, if we needed to find the coordinate, we would just plug 1/2 into the original function and simplify down to figure out the y coordinate of that inflection point. Let's go ahead and look at another example. All right, I'm going to go ahead and have you pause the video and try and work through this example on your own. Find the first and second derivative, make your sign chart with the second derivative, and fill out the information on the right. Then unpause the video and see how you did. So hopefully you had time to get started. Here are our derivatives. And then I'm going to go ahead and set the second derivative equal to 0 and solve for x. That's going to give me two possible inflection points, one at 3 pi over 4 and one at 7 pi over 4. That's where sine and cosine are the same, but their sign is opposite. Then we're going to go ahead and make a sign chart with those values. On this sign chart, we can actually include endpoints because we're not going on forever. We're being asked solely about concavity on these closed intervals. So go ahead and check your sign chart. And then we can fill out our concavity intervals based on where the second derivative is positive and negative. Make sure you stop at 0 and 2 pi. You don't go all the way to negative or positive infinity since we are on a closed domain. So there we have our concavity intervals. We're going to have inflection points at both of our possible inflection point values at x equals 3 pi over 4 and x equals 7 pi over 4, since the second derivative, g double prime of x, changes sign at both of those values. So now that we've seen how the second derivative can tell us about concavity and where we're changing concavity, we're going to extend this idea and see how that second derivative and concavity can help us identify relative extrema, which is something that we learned in the last section. Okay, the second derivative test for relative extrema actually allows us to not have to do all the extra work that we do with the first derivative to find relative extrema, but to use what we know about concavity to determine extrema. So if I know that a function is concave up and the first derivative is equal to 0, that would mean that I must have a relative minimum there. If I know that a function is concave down and I know that there's the first derivative is equal to 0, that would mean it must be a relative maximum. So if we can identify where the first derivative is 0 and whether it's concave up or concave down there, then we can use that to determine relative extrema. So this test does not give us any information about inflection points. It allows us to find relative extrema using the second derivative. So what we're going to do is find the first derivative and find the critical numbers. That's going to be step 1. We're going to plug those numbers into the second derivative to determine the concavity. And then we're going to determine, based on the concavity and the first derivative being 0, if we have a relative maximum or minimum there. So let's go ahead and look at this example. Go ahead and find the first derivative and the critical numbers, and then find the second derivative. All right, so here we have our first derivative and the critical values, the numbers that make the first derivative 0, and then we have our second derivative. So instead of making a sign chart to talk about relative extrema, we are going to plug these 3 critical numbers into the second derivative to figure out if the output is positive or negative. So if we plug in 0, f double prime of 0 is going to be 12, which is positive, which means the function is concave up there. If we plug in negative 1, we're going to get negative 36 plus 12, which is negative, so it's going to be concave down there. If we plug in positive 1, we're going to get negative 36 plus 12, which is negative, so it's going to be concave down there. So what we know is 2 things. The first derivative is 0, and the second derivative, being positive or negative, tells us the type of extrema. So how we're going to write that is f has a relative minimum at x equals 0 since there's two things here, f prime of 0 is 0 and f double prime of 0 is positive. So we're saying the first derivative is 0 and the second derivative is positive, so it's concave up. Similarly, f has relative max at two places at x equals plus or minus 1, since f prime of negative 1 equals f prime of positive 1, which is 0, and f double prime of negative 1 and f double prime of positive 1 are both less than 0, so concave down. So this is how we can use the second derivative to determine if a critical value is a relative extrema. One thing I want to point out is that if, when we were doing this, we got that the second derivative was equal to 0, that would mean there's no concavity there, and we wouldn't be able to use this to determine relative extrema. Let's look at a couple more examples and then wrap up this video. All right, let's go ahead and look at number 3 together, and then I'll have you try number 4 on your own. Step 1, find the first derivative, 3x squared minus 6x. Determine where it is 0. So our critical numbers are going to be 0 and 2. We're going to find the second derivative, which is going to be 6x minus 6, and we're going to plug those two values into the second derivative to determine the concavity at those values. So if we plug in 0, we get negative 6, so we're going to have a relative max when x is equal to 0. If we plug in 2, we're going to get 12 minus 6, which is positive 6, so we're going to have a relative min. And again, when we write our justifications, we need to indicate the first derivative of that value is 0 and the second derivative of that value is positive or negative. So go ahead and pause the video and write your justifications. And there we have our justifications. So go ahead and pause the video, do number 4 all the way on your own, and then unpause the video and see how you did. So our first derivative is going to be negative 2x plus 2. That's going to have a critical number when x is 1. Our second derivative is actually just negative 2, which means we are always concave down, which means y has a relative maximum at x equals 1, since y prime of 1 is equal to 0 and y double prime of 1 is less than 0. Also, if you think about this, this is a quadratic and it opens upside down. So it makes sense that it's never changing concavity. It's always concave down and it has a relative maximum. So don't forget all the things you have learned in other classes. They can help you out here. All right, last but not least, number 5, we are given a table of values with information about the first and second derivative. So we know we will have relative extrema if the first derivative is 0. So I'm going to check that first. So I don't have any relative extrema when x is equal to 2 because the first derivative is not 0. The first derivative has to be 0, and then whether we're positive or negative is going to give us information about what type of extrema. So the first derivative is 0 when x is equal to 3, and the second derivative is positive, so that's going to be concave up. We're going to have a relative minimum there. When x is negative 1, the first derivative is 0 and the second derivative is negative, which means concave down, which means we're going to have a relative max there. When x equals to 0, the second derivative is also 0, which means we don't know. There could be a relative extrema there, but we don't know because there isn't any concavity. So we can only draw conclusions about what's happening at negative 3, negative 1, and positive 2. So go ahead and write your conclusion using the justifications and then unpause the video and see how you did. And there we have our conclusion. Let's go ahead and wrap up this video. In this lesson, we covered 3.4. We talked about what concavity is, the curvature of the graph, whether it's curving upward and making a C shape or a cup shape, or curving downward and making a frown shape. That's the concavity. We talked about how to use the second derivative to determine the concavity of the original function, and how when it's changing concavity, that's called an inflection point. And we lastly talked about how to use that concavity to identify a relative extrema. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.